Hi everyone, my name is Jason Patrick. Welcome to this free technical training session on soil drying for high voltage cable ampacity calculations. Here's an outline of the presentation. I will briefly introduce ELEK cable HV software which was used for the modeling. I will talk about IEC 60287 and the CIGRE current rating calculations. I'll talk about soil thermal resistivity and the fundamentals of soil drying. I'll talk about soil dryout prevention measures, Windfarm landfall problem, the models for soil drying calculations. I'll talk about the two-zone soil drying model and the new multi-zone model. And I will present two calculation examples with some slides as well as a software demonstration of how to perform the calculations. Finally, I will draw some conclusions and recommendations. ELEK cable HV software is accurate and validated software for cable current rating calculations. It's suitable for any AC voltage from low voltages up to high voltage, including HVDC. It fully complies with IEC 60287 and can perform calculations for your custom cables under your specific installation conditions. It is extremely accurate and has been fully validated. You can request and download a free trial from elek.com. IEC 60287 is the penultimate standard for cable current rating calculations. It is still commonly used because for the following reasons, because it can be adapted to common cable types and installation methods. It is regarded as accurate and reliable, and it produces consistent and comparable results. There are 9 parts to the standard. It is fairly complicated. The calculations are quite ambiguous and difficult to implement. I'll talk about CIGRE Technical Brochure 880. This technical brochure came about recently because the calculations being performed according to IEC 60287, when different engineers produced calculated results, they were getting different answers. So this working group was formed to fix some of the ambiguities, and it provides 17 calculation examples, 49 guidance points, and should be used as a verification or validation procedure for calculation tools. That's its intention. We have used this technical brochure to validate our software. We can calculate every single example, and we have the highest accuracy possible, which is matching results to 11 decimal places. This technical brochure reflects the views of the current best practice in cable current rating calculations. We also provide finite element calculations, which is a little bit different and the subject of another presentation. Soil thermal resistivity. For buried cable ratings, the most important parameters are soil thermal resistivity of the native soil or the backfill if applicable, and soil temperature at burial depth, which is closely linked with Earth's surface temperature or ambient air temperature. Soil actually contributes the largest single thermal resistance and the largest thermal capacitance to buried cables. Thermal resistivity of the soil depends on the soil type, moisture content, and soil density. Controlled backfills are often can be used and often significantly increase ampacity. In the top right-hand corner of this slide, you will see some sample thermal resistivity values taken from IEC 60287, but I highly recommend that you use measured values. And you can see in the image there is a person taking thermal resistivity measurements inside a trench. Soil thermal resistivity has a significant impact on cable ampacity. It doesn't affect the native soil thermal resistivity, has less of an effect on cables that are installed in backfill, but it's still significant and certainly has a significant effect on direct buried cables. Soil drying around cables. Heat from cables may cause significant moisture migration away from cables. The main cause is the temperature gradient, which comes from the cable and transfers through the soil. A dry soil zone may develop around the cables. There is a sharp transition from low resistivity to high resistivity as drying occurs. It should be noted that soil moisture migration is a dynamic process that is extremely complicated. On the right-hand side, you'll see a soil temperatures plot. And in the middle of the plot, you'll see the cables, which are the source of the heat, and surrounding the cables, in this case, is a backfill. What are the potential negative impacts of soil drying? The external thermal resistance significantly influences cable ampacity, accounting for over 70% of the temperature increase in buried cables. So the external thermal resistance consists of the external thermal environment, which is dictated by soil thermal resistivity in the case of buried cables. The outer cable surface is typically within the range of 50 to 70% of conductor temperature. Therefore, drying can certainly occur. If a dried out zone forms around the cables, an abrupt rise in cable temperature may cause thermal runaway, leading to damage of cables. There are two famous cases. There was one in Auckland in 1998, leading to a cable failure. And again, more cable failures in London in 1962. The investigation, a statement from the investigation is shown in the right-hand side, which reads, "It is now suspected that the soil thermal resistivities are higher than the figures used to calculate the ratings for these cables, and that cables may therefore have been overloaded." Soil drying out can be prevented or at least reduced. The effects can be reduced using such measures as a controlled backfill, installing that around the cables, potentially increasing the installation depth to reach more thermally stable soils, using a flat cable arrangement, flat and spaced, instead of a trefoil formation, or at least a spaced arrangement to distribute the heat over a larger area in the soil and not concentrate it, as well as distributed temperature sensors or optical fibers within the cable to detect hotspots as they arise before any irreversible damage to the cable insulation occurs. Here's an interesting application, which is Windfarm Landfall. You can see, and the potential soil dry out zone. This zone, which is circled in red, is really can become the bottleneck to the wind farm generation supply because it's an area where the cable is deeply buried above the water table, so the soils are not saturated. They can and often do dry out, and leading to a reduced cable current carrying capacity. And it, as I said, it becomes the thermal bottleneck for the installation. There are different models used for calculating soil drying conditions surrounding cable ampacity calculations. There is the two-zone method for the steady state and dynamic ratings. And there is the finite element method combined with a dynamic moisture migration model. So the two-zone steady state method it comes from IEC 60287 or the CIGRE Electra 104 document. And the dynamic transient rating method that incorporates soil drying comes from IEC 60853-3. And there are three sub-methods for the transient calculations. The advantages of these two-zone methods are that they do not require detailed soil information. However, they do require thermal resistivity measurements of the native soil at ambient and full wet moisture content conditions and when the soil is fully dry. The disadvantages are that these methods, the two-zone method can be overly simplistic and under certain conditions. It does not consider the initial soil moisture content, which can be important, unlike the dynamic moisture model. The finite element method and the dynamic moisture migration model is based on modified Philip and DV's equations. The advantages are that it can deal with steady state and time varying currents. It is more accurate, obviously, but it's more complicated to implement, and it requires very detailed information about the soil under different environmental conditions, and it requires essentially laboratory testing of the soil. Let me explain the two-zone soil drying model. So you can see the image on the right-hand side. Moist soil is assumed to have a uniform soil thermal resistivity. That's on the outside of that blue circle. Heat dissipated from a cable causes its surface temperature to rise above a critical limit. The surrounding soil will dry out, creating a zone having a uniform thermal resistivity, which is higher than the moist soil resistivity or the original. The dry soil zone boundary is isothermal. These are the current rating equations from IEC 60287. The top one is without soil drying, and the second equation shown here is the modified first equation that allows you to consider or incorporate soil drying out. So you've got the factors V and delta theta X, and to calculate those values, you need soil thermal resistivity of the dry soil, and you need soil thermal resistivity of the moist soil, and you need the soil's critical temperature rise at the boundary between the dry and moist soil zones, which I will explain. The critical soil temperature is defined as where the soil thermal resistivity starts to change significantly due to moisture loss. It is highly dependent on the initial moisture content of the soil. A typical, very common value used for this critical temperature rise is, or temperature limit is 50 degrees Celsius, but this is not explicitly stated in IEC 60287. The German standard VDE 0276-1000 does provide a simple equation for calculating critical temperature rise or critical temperature limit for soil drying. The good thing is that it incorporates load factors, so it does consider cyclic loading. We have implemented this method in our software. Electra 145 provides typical critical temperature rise values for different soil types, including sandy clay, sandy soil, crushed rock, and some selected sands. There are some critical values shown in the table here. There is an equation for the critical soil temperature rise taken from Electra 145. It's relatively simple, but it does require more information about the soil. It's the critical SCR, the critical degree of saturation of the soil, that needs to be determined, and that can only be determined, or the easiest way to determine it is by taking a soil sample and plotting soil moisture or saturation versus thermal resistivity. Now, if that plot has an asymptote or a flat point, then the critical degree of saturation is where the rise is 10% above the asymptote, and that can be used as a value for SCR. But again, it requires you to take a measurement sample of the soil and to perform these tests in a laboratory. The problem is you've got curve B there. If the soil type doesn't produce, or this measurement doesn't produce an asymptote, then you can't use this method to determine SCR. And there are other methods explained, more complicated methods explained in that brochure. There is a few slides now which explain the derivation of the IEC method for incorporating the two-zone soil dry-out model within the IEC equations. I'm not going to go through in detail. through the derivations, but I will present the slides here and the steps, and you feel free to pause the presentation and go back over the derivations. But ultimately, we arrive at that IEC current rating calculation equation, which incorporates the factors V and delta theta X. But there are some limitations to this equation for dealing with partial soil dryout and incorporating the two-zone model as follows. The IEC equations can only be used, or the IEC two-zone method can only be applied to single isolated cables or circuits. It can only be applied to cables operating at unity load factor, so not cyclic loads. And it applies only to direct buried, no backfills, at standard burial depths. So the circuit on the left-hand side, or the installation of a single circuit or a single cable, that's okay to deal with using the IEC method for considering soil dryout around the cables. But in the bottom right-hand corner, you'll see a more complicated installation. You've got multiple circuits installed in ducts within a backfill, and the load factor could be non-unity. So how do you deal with that type of installation when you want to or need to consider soil drying out? So ELEK has developed this multi-zone model. It's actually a world first. And this method extends the IEC limitations, allowing you to consider soil dry out along with cyclic loading, backfill and or duct enclosures, and multiple circuits, or completely simultaneously. The model is shown here. It's quite a bit more complicated than the simple IEC two-zone method. There's also quite a significant assumption in the IEC standards related to backfills. That assumes the cables within a backfill are located in the center of the backfill. Often they are not. And that all cables within a backfill are carrying the same current, dissipating the same losses into the backfill, which is not the case very often. So ELEK has extended the IEC methods, so therefore we consider the exact cable positions, different cable types, different cable loadings within a backfill, and we properly apply the backfill corrections to the calculations. This can result in a 10% difference in the cable rating calculations provided by the IEC method and the more accurate ELEK method. Right now, I'm going to go through a couple of practical examples. The first example, I'm going to use a few slides, and then I'm going to demonstrate that example within the software. So here the example consists of multiple buried circuits. Now, to consider soil dryout, we need to use the ELEK method, which we will do. So there are 4 33 kV circuits. On the left-hand side, these are directly buried circuits. On the right-hand side, you've got these 4 circuits buried in a backfill. There are the native soil, the backfill thermal resistivity, and the dry soil thermal resistivity when dryout occurs at a critical temperature. Those two values are given, which work with the two-zone model as well as the ELEK method model, multi-zone model. And the load factor is varied from 1 down to 0.75, which again requires the ELEK method. Let's look at soil temperatures. Now, if we, with soil drying considered, the soil around the cables becomes hotter. You'll notice on the left-hand side, we've got soil temperature plots without soil dryout being considered. And on the right-hand side, we've got the same cases where soil dryout is being considered. Now, what we're doing is we are fixing the load current for all of the circuits, and we are just turning soil dryout on or off. You'll see that the soil temperatures get hotter. That's more red. And for directly buried cables, there's even more red compared to the backfill. That's because the backfill keeps the cables relatively cooler. So if you don't consider soil dry out, you may get a nasty surprise that your cable temperatures exceed their limits, leading to cable thermal runaway. This is a plot of for the multiple circuits cases for directly buried and in backfill with or without soil drying out. So the current ratings for the cables in backfill are higher, the two top curves, and the buried circuit ratings are the bottom two plots. As the loading or the cyclic load factor is reduced from unity, so the cables are effectively not fully loaded, then the current rating of the cables goes up. Are reduced with intermittent loading or cyclic loading. Now for this calculation example, I'm going to show you how to perform the calculations using software. So we've got the first case, which is the 4 buried circuits directly buried, same cable type, and they are arranged in the trefoil arrangement. So I can select the circuits, I can move them around anywhere I like, and the calculation results are updated live. The main inputs for a buried installation include the native soil thermal resistivity, the ambient soil temperature, the circuits are defined, each of the circuits, and the cable type for that circuit. There is a soil temperature plot. If I make changes here, I will see that the temperature plot is updated along with the calculations. Detailed calculation results are shown on the right-hand side. This is a combined system with a combined current rating of 1,920 amps. And the detailed electrical loss calculations and thermal calculations are on the right-hand side, which can be shown in a report. So I'll just return that circuit back to where it was roughly. I can move it around with the mouse. I can also define exact using the numerical inputs. And there is a soil dry out tab. So you'll notice the current rating of the 4 circuits. The 2 circuits in the middle have a lower current rating. Those are more affected by the mutual heating by all circuits. So 500, 435 amps rating for the inner circuits. If I turn soil drying on, that rating should go down quite significantly. So these are the settings for soil dry out. So the dry thermal resistivity setting is 2.5 and the critical temperature is 50 degrees. And we can re-look at the soil temperature plot. So we actually have lower soil temperatures when we consider soil dryouts, and the current rating is reduced. Down the bottom of the screen, you can see I actually have two tabs here. The software is functions quite similarly to Excel, where you can have multiple tabs. So I have a different installation condition in section 2 or tab 2. So this time I've got the 4 buried circuits called in a backfill. So I can adjust the size of the backfill, the position of the backfill on the user interface. Otherwise, I can explicitly specify the dimensions and the properties of the backfill using the numerical controls. So this time soil dryout is turned off. Let's have a look at the soil temperature plot. Actually, you will see the hottest point on the backfill is marked. And in this case, you can see that temperatures well exceeding 50 degrees are outside of the backfill area. So let's turn soil drying on and we will see the current ratings go down. But again, we still have soil temperatures exceeding 50 degrees. So what we would expect is that outside of the backfill, in this case, the soil is going to dry out and leading to potentially higher soil temperatures. So there is a special feature within the software, which is soil dryout prevention, to avoid or to limit the temperatures outside of the backfill. and we simply select prevent soil drying outside of backfill, and the software will adjust the current rating such that the temperatures outside of the backfill do not exceed 50 degrees. So you can see that the 50-degree isotherm is confined to be within the thermally stable backfill. And again, to achieve that, we needed to reduce our current rating. In the next example, I'm going to discuss soil dryout prevention using a practical real-world example. So I'm showing you on this slide the Ausgrid, which is a power utility here in Australia, quite a famous one, and their standard, which is quite typical, provides quite a typical set of requirements for around the world, where they are telling you how to design their cable trenches to consider or incorporate soil drying. So let me just read this paragraph. Ausgrid assumes soil dryout will begin when the native soil is exposed to a temperature of 50 degrees. So they're using that 50-degree assumption. This is very, very common. It is acknowledged this is a moderate position, and some locations with sandy soils dry out at a temperature lower than this. Yes, it's believed that native sandy soils will dry out at a temperature below 50 degrees, so it could be 40 degrees, for example. Thermal stability shown via 50 degrees isotherm modeling should be included in the ratings report, so you'll need to use software for that. One way to manage the risk of dryout is to ensure the 50-degree isotherm is fully within the thermal stable material. So here in the diagram, you've got a cross-section of a trench. You've got 3 cables installed in a thermal backfill. That has a good dry thermal resistivity at 0-degree moisture content. It's reliable, it's stable. Now, you can see that in this example, the 50-degree isotherm extends outside of that backfill into the moist or native soil. Now, it's expected that that soil will dry, and the thermal resistivity of that soil will increase significantly. So to avoid that, we can use this method, which is soil dryout prevention, and that is explained by the standard, which is to restrict the 50-degree isotherm to be within the confines of the backfill material. And now I'm going to show you how to do in this example. I'm going to show you how to do that in the software. Here is the second example in the software. So we've got a single 132 kV circuit installed in ducts in a flat and spaced arrangement. We've got a single backfill here. So the current rating using solidly bonded sheaths is provided. It's 630 amps. Let's have a look at the electrical losses. We can see there's a sheath circulating current of 274 amps in this case when the sheath is solidly bonded. Let's look at the same conditions when we're using single point bonded. So the current rating of the cables rises significantly because we have little to no sheath circulating current, and however, we do have a sheath standing voltage as shown here. So a significantly higher current rating, 630 amps compared to 900 amps. Now let's look at soil dryout. So for the same solidly bonded case, if we consider soil dryout, let's look at the soil dryout tab. We'll turn off soil dryout prevention. So if we consider soil dryout, there's a bit of a reduction in current capacity of the cable, so 630 compared to 600 amps, and a reduction of 30 amps for this solidly bonded case, just caused by the soil drying out. Now the backfill, as we've mentioned, is protecting the cables somewhat from soil dryout, but it's still having an effect. And the standard criteria are here for the soil drying. Let's look at the soil temperature plot. So we still have the temperatures of the soil exceeding 50 degrees outside of the backfill. If we wanted to limit that, we could use this soil drying prevention or backfill. So let's turn that on, and our 50-degree contour should be restricted within inside the backfill. To achieve this, we need to reduce the current rating further. So we went from 600 down to 550 amps for the rating of the cable. And to achieve that, we need to operate the conductor temperature, which is shown here at 75.7 degrees. So something less than the maximum conductor allowable operating temperature of 90 degrees. Let's look at the same case for the single point bonded circuit. So with soil drying out compared to 900 amps, now we've reduced the current rating down to 835 amps. If we're considering soil dry out, let's look at the soil temperature plot. The hottest point is marked. We have temperatures exceeding 50 degrees outside of the backfill. Oh, no, we don't actually. My apologies. Soil dry out prevention was turned on. We had everything above 50 degrees was confined within the backfill. So that rating of 835 amps was actually with soil dry out prevention of the backfill. So we had 900 amps compared to 870 amps. And now if we prevent soil drying outside of the backfill, so we limit the 50-degree contour to be within inside the backfill, we have this result of 835 amps. So that's how we can use the soil drying calculations and the soil dry out prevention calculation methods within ELEK Cable HV software. Thank you so much. So I'll finish the presentation with some conclusions and recommendations. Considering soil drying out helps designers to better evaluate the worst thermal conditions of buried cables. Adding a backfill can significantly improve the heat dissipation of the environment of the buried cables. The two-zone soil dry-out model is sufficiently accurate for steady-state calculations where detailed soil information is unavailable. The IEC standard provides a two-zone method that has too many limitations, making it completely impractical to use. You remember I mentioned those limitations: a single circuit, no backfill, no ducts, and a unity load factor only, no cyclic loading. The following recommendations apply. Always consider soil dry out for your buried cable ampacity calculations. There's no exceptions really. Make use of advanced modeling techniques such as those developed by ELEK. Our model allows simultaneous consideration of multiple circuits, considering soil dry out, cyclic loading, backfills, and duct enclosures, and applies soil dry out prevention modeling techniques as required. Thank you so much for attending this free technical training. I'll see you on the next one.